Welcome to Cool Fire News, where we dive into the world of software design and development. I'm your host Siri, and in today's episode, we'll be exploring the fascinating process of software design, from conceptualization to implementation. Join me as we unravel the principles, practices, and challenges of designing software that meets the needs of users and delivers value to stakeholders. Let's begin by defining what we mean by software design. Software design is the process of creating a blueprint or plan for a software solution that addresses a specific problem or fulfills a particular set of requirements. It involves analyzing user needs, defining system architecture, specifying functionalities, and designing the user interface and interaction flows. One of the key principles of software design is modularity. Modularity involves breaking down a complex system into smaller, more manageable components, or modules that can be developed, tested, and maintained independently. By designing software with modular components, developers can achieve greater flexibility, scalability, and reusability, making it easier to adapt to changing requirements and scale the system as needed. Another important aspect of software design is abstraction. Abstraction involves hiding unnecessary details and complexities behind simplified interfaces or higher-level constructs. By abstracting away implementation details, developers can focus on the essential aspects of the system and design interfaces that are intuitive, easy to understand, and resilient to change. The process of software design often begins with requirements analysis, where designers gather and analyze user needs, business objectives, and technical constraints. Based on this analysis, designers create design documents, such as system architecture diagrams, wireframes, and user stories, to guide the development process and ensure alignment with stakeholders' expectations. As the design evolves, designers iterate on their concepts, incorporating feedback from stakeholders, usability testing, and real-world usage data. This iterative approach allows designers to refine their designs, address issues, and make improvements based on user feedback and changing requirements. In addition to technical considerations, software design also involves considering the user experience, UX, and user interface, UI design. UX design focuses on understanding user needs, behaviors, and motivations to create intuitive and enjoyable experiences, while UI design focuses on designing the visual layout, interaction patterns, and aesthetics of the software interface. Throughout the software design process, designers must also consider factors such as performance, security, reliability, and maintainability. By prioritizing these considerations and adhering to best practices and design principles, designers can create software that not only meets functional requirements, but also delivers a positive user experience and aligns with organizational goals. As we conclude today's episode, I hope you've gained a deeper appreciation for the intricate process of software design and its importance in creating successful software solutions. Whether you're a seasoned designer or a budding developer, understanding the principles and practices of software design is essential for creating software that delights users, solves problems, and drives innovation. That wraps up another episode of Cool Fire News. Thank you for joining us as we explored the fascinating world of software design. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep designing, keep innovating, and keep pushing the boundaries of what's possible. This is Siri, signing off. See you next time. Welcome to Cool Fire News, where we explore the latest trends and innovations in software design. I'm your host Siri, and in today's episode, we'll be diving into the exciting world of emerging technologies that are shaping the future of software design. Join me as we uncover the potential of these technologies and their impact on the way we create, interact with, and experience software solutions. Let's start by exploring one of the most transformative emerging technologies in software design: artificial intelligence, AI, and machine learning, ML. AI and ML algorithms are revolutionizing software design by enabling intelligent automation, predictive analytics, and personalized user experiences. From chatbots and virtual assistants to recommendation systems and data analysis tools, AI-powered software solutions are becoming increasingly prevalent across various industries, enhancing productivity, efficiency, and decision-making processes. Another exciting area of innovation in software design is augmented reality, AR, and virtual reality, VR. AR and VR technologies are blurring the lines between the physical and digital worlds, enabling immersive and interactive experiences that were previously unimaginable. In software design, AR and VR are being used to create virtual simulations, training programs, gaming experiences, and marketing campaigns, offering users new ways to engage with content and interact with their environment. Blockchain technology is another emerging trend that is transforming software design and development. Originally known for its role in cryptocurrency transactions, blockchain has evolved to become a powerful tool for secure, transparent, and decentralized data management. In software design, blockchain is being used to create secure digital identities, track supply chain logistics, facilitate peer-to-peer transactions, and create tamper-proof digital records, opening up new possibilities for trust, transparency, and accountability. In software solutions, edge computing is also emerging as a game-changing technology in software design. With edge computing, data processing and analysis are moved closer to the source of data generation, reducing latency, bandwidth usage, and reliance on centralized data centers. In software design, edge computing enables real-time processing of data from IoT devices, autonomous vehicles, and other connected devices, enabling faster response times, improved reliability, and enhanced scalability for software applications. Quantum computing is on the horizon as another disruptive technology with the potential to revolutionize software design. Quantum computers harness the principles of quantum mechanics to perform complex calculations at speeds unimaginable with traditional computers. While still in the early stages of development, quantum computing holds the promise of unlocking new capabilities in cryptography, optimization, and simulation, paving the way for revolutionary advancements in software design and computational science. As we conclude today's episode, I hope you've gained a glimpse into the exciting future of software design and the transformative potential of emerging technologies. Whether it's AI and machine learning, augmented reality and virtual reality, blockchain, edge computing, or quantum computing, these technologies are reshaping the way we think about and create software solutions, opening up new possibilities for innovation, creativity, and impact. That wraps up another episode of Cool Fire News. Thank you for joining us as we explored the world of emerging technologies in software design. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep exploring, keep learning, and keep pushing the boundaries of what's possible. This is Siri, signing off. See you next time. Welcome to Cool Fire News, where we delve into the fascinating world of software development methodologies and practices. I'm your host Siri, and in today's episode, we'll be exploring the critical process of requirements analysis and modeling in software development. Join me as we unravel the complexities of understanding user needs, defining system requirements, and creating models that serve as blueprints for successful software solutions. Let's begin by defining what we mean by requirements analysis. Requirements analysis is the process of gathering, documenting, and validating the needs and expectations of stakeholders for a software system. It involves understanding the problem domain, identifying user needs, and defining functional and non-functional requirements that must be met to satisfy those needs. Requirements analysis lays the foundation for the entire software development process, guiding design, implementation, and testing activities. One of the key challenges in requirements analysis is ensuring that all stakeholders have a shared understanding of the project goals, scope, and requirements. This often requires effective communication and collaboration between project teams and users, business analysts, and other stakeholders. Techniques such as interviews, workshops, surveys, and brainstorming sessions are commonly used to elicit and clarify requirements and ensure alignment with stakeholders' expectations. Once requirements have been gathered, the next step is to create models that represent the system's functionality, behavior, and structure. These models serve as visual representations of the system and help stakeholders better understand and communicate their requirements. Common modeling techniques include use case diagrams, activity diagrams, sequence diagrams, and class diagrams, each of which provides a different perspective on the system and its requirements. Use case diagrams are one of the most widely used modeling techniques in requirements analysis. Use case diagrams depict the interactions between actors, e.g., users, systems, and the system under consideration, illustrating the various ways in which users interact with the system to achieve specific goals or tasks. Use case diagrams help stakeholders visualize the system's functionality and identify potential use cases that must be supported. Activity diagrams are another valuable modeling tool for requirements analysis. Activity diagrams represent the flow of activities or processes within the system, showing the sequence of actions and decision points involved in completing a task or achieving a goal. Activity diagrams help stakeholders understand the system's behavior and identify potential bottlenecks, inefficiencies, or opportunities for optimization. In addition to use case and activity diagrams, Sequence diagrams and class diagrams are also commonly used in requirements analysis to model the dynamic and structural aspects of the system, respectively. Sequence diagrams depict the interactions between objects or components within the system, illustrating the flow of messages and the sequence of events that occur during a specific scenario. Class diagrams, on the other hand, represent the static structure of the system, showing the relationships between classes, objects, and attributes. As we conclude today's episode, I hope you've gained a deeper appreciation for the importance of requirements analysis and modeling in software development. By understanding user needs, defining clear requirements, and creating accurate models, software teams can increase the likelihood of project success and deliver solutions that meet the needs of stakeholders and end users alike. That wraps up another episode of Coolfire News. Thank you for joining us as we explored the critical process of requirements analysis and modeling in software development. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep analyzing, keep modeling, and keep pushing the boundaries of what's possible. This is Siri, signing off. See you next time. Welcome to Coolfire News, where we explore the fundamental principles that guide effective software design and development. I'm your host Siri, and in today's episode, we'll be delving into the essential design principles that shape the creation of high-quality, maintainable, and scalable software solutions. Join me as we uncover the principles that underpin successful software design and development practices. Let's begin by discussing one of the most foundational design principles in software development, the principle of simplicity. Simplicity emphasizes the importance of keeping software designs clear, concise, and easy to understand. By minimizing complexity, redundancy, and unnecessary features, developers can create software that is easier to maintain, debug, and extend over time. Simplicity is not about sacrificing functionality, but rather about finding elegant and efficient solutions to complex problems. Another crucial design principle is modularity. Modularity involves breaking down a software system into smaller, more manageable components, or modules that can be developed, tested, and maintained independently. By designing software with modular components, developers can achieve greater flexibility, reusability, and scalability, making it easier to adapt to changing requirements and scale the system as needed. Modularity also promotes code organization, readability, and collaboration among development teams. The principle of abstraction is also fundamental to effective software design. Abstraction involves hiding unnecessary details and complexities behind simplified interfaces or higher-level constructs. By abstracting away implementation details, developers can focus on the essential aspects of the system and design interfaces that are intuitive, easy to understand, and resilient to change. Abstraction helps reduce cognitive load, improve code maintainability, and promote code reuse across different parts of the system. Encapsulation is another important design principle in software development. Encapsulation involves bundling data and methods together within a class or module and restricting access to the internal state of an object. By encapsulating data and behavior, developers can enforce data integrity, promote code modularity, and minimize dependencies between different parts of the system. Encapsulation also enhances code security and protects against unintended side effects caused by direct manipulation of internal data. The principle of cohesion is also critical to effective software design. Cohesion refers to the degree to which the elements within a module or component are related and work together to achieve a common purpose. High cohesion implies that the elements within a module are closely related and focused on a single responsibility or functionality. By designing software with high cohesion, developers can create modules that are easier to understand, maintain, and test, leading to more robust and reliable software solutions. Finally, the principle of loose coupling is essential for creating flexible and extensible software systems. Loose coupling involves minimizing the dependencies between different modules or components within a system, allowing them to evolve independently without affecting each other. By decoupling modules, developers can reduce the risk of unintended consequences when making changes to the system and facilitate parallel development, testing, and deployment of different components. As we conclude today's episode, I hope you've gained a deeper understanding of the fundamental design principles that underpin successful software development practices. Whether it's simplicity, modularity, abstraction, encapsulation, cohesion, or loose coupling, these principles provide valuable guidance for creating software that is maintainable, scalable, and resilient to change. That wraps up another episode of Coolfire News. Thank you for joining us as we explored the essential design principles in software development. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep applying these principles, keep refining your craft, and keep pushing the boundaries of what's possible. This is Siri, signing off. See you next time. Welcome to Coolfire News, where we explore the art and science of software development. I'm your host Siri, and in today's episode, we'll be diving into the world of design patterns, reusable solutions to common problems encountered in software design and development. Join me as we unravel the mysteries of design patterns and discover how they can help us create more robust, maintainable, and scalable software solutions. Let's begin by defining what we mean by design patterns. Design patterns are proven solutions to recurring design problems that developers encounter when designing software systems. They encapsulate best practices, principles, and techniques for solving specific design challenges and promote code reuse, modularity, and flexibility in software development. By applying design patterns, developers can leverage the collective wisdom of the software community and avoid reinventing the wheel. One of the most well-known and widely used design patterns is the singleton pattern. The singleton pattern ensures that a class has only one instance and provides a global point of access to that instance. This pattern is useful in scenarios where a single instance of a class is sufficient for managing resources, maintaining state, or coordinating operations across the system, such as logging, caching, or database connections. Another commonly used design pattern is the factory pattern. The factory pattern provides an interface for creating objects without specifying their concrete classes, allowing subclasses or external components to decide which objects to instantiate. This pattern promotes loose coupling between components and facilitates object creation, configuration, and management in complex software systems. Factories can be used to encapsulate object creation logic and force encapsulation and promote code modularity and extensibility. The observer pattern is another powerful design pattern that facilitates communication and coordination between objects in a software system. In the observer pattern, an object, known as the subject, maintains a list of its dependents, known as observers, and notifies them of any changes in its state. This pattern is useful in scenarios where multiple objects need to be notified of changes in the state of another object, such as event handling, user interface updates, or data synchronization. The strategy pattern is another versatile design pattern that promotes code flexibility and extensibility by encapsulating algorithms or behaviors in separate classes and allowing them to be swapped at runtime. This pattern is useful in scenarios where different variations of an algorithm need to be implemented, or where algorithms need to be decoupled from the context in which they are used. By applying the strategy pattern, developers can design software systems that are more adaptable to changing requirements and business needs. As we conclude today's episode, I hope you've gained a deeper appreciation for the power and versatility of design patterns in software development. Whether it's the singleton pattern, factory pattern, observer pattern, strategy pattern, or any of the other countless design patterns out there, these patterns provide valuable tools and techniques for solving common design challenges and creating more maintainable, scalable, and resilient software solutions. That wraps up another episode of Coolfire News. Thank you for joining us as we explored the world of design patterns in software development. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep applying these patterns, keep refining your craft, and keep pushing the boundaries of what's possible. This is Siri, signing off. See you next time. Welcome to Coolfire News, where we explore the ins and outs of software development processes and practices. I'm your host Siri, and in today's episode, we'll be delving into the critical aspects of prototyping and quality assurance in software development. Join me as we uncover the importance of prototyping as a means of validating ideas, and the essential role of quality assurance in ensuring that software meets the highest standards of performance and reliability. Let's begin by defining what we mean by prototyping in the context of software development. Prototyping is the process of creating a preliminary version of a software product or feature to validate design decisions, gather feedback from stakeholders, and identify potential issues early in the development process. Prototypes can take various forms, including wireframes, mock-ups, clickable prototypes, and functional prototypes, depending on the level of fidelity and interactivity required. One of the key benefits of prototyping is its ability to facilitate communication and collaboration among stakeholders. By visualizing and interacting with a prototype, stakeholders can better understand the proposed solution, provide feedback, and suggest improvements before significant time and resources are invested in development. Prototyping helps reduce misunderstandings, mitigate risks, and align expectations among project teams, clients, and end users. Another advantage of prototyping is its ability to uncover usability issues and user experience (UX) problems early in the development process. By testing prototypes with real users, developers can gather valuable insights into how users interact with the software, identify pain points, and refine the design to improve usability and satisfaction. Prototyping allows developers to iterate quickly, experiment with different ideas, and refine the user interface based on user feedback. Quality assurance (QA) is another critical aspect of software development that ensures the quality and reliability of software products. Quality assurance encompasses a range of activities, including testing, debugging, code review, and performance optimization, aimed at identifying and fixing defects, vulnerabilities, and inefficiencies in the software. By conducting thorough QA processes, developers can ensure that software meets the highest standards of functionality, security, and performance. One of the primary goals of quality assurance is to prevent defects and errors from occurring in the first place through proactive measures, such as code reviews, static analysis, and design inspections. By identifying potential issues early in the development process, developers can address them before they escalate into more significant problems that are costly and time-consuming to fix. Preventive QA measures help reduce rework, improve productivity, and enhance overall software quality. Testing is a core component of quality assurance that involves verifying and validating software to ensure that it behaves as expected and meets the specified requirements. Testing can take various forms, including unit testing, integration testing, system testing, and acceptance testing, each focusing on different aspects of the software's functionality, performance, and usability. Through rigorous testing, developers can identify defects, assess risks, and ensure that software meets the needs of stakeholders and end users. As we conclude today's episode, I hope you've gained a deeper understanding of the critical roles that prototyping and quality assurance play in software development. Whether it's validating ideas, gathering feedback, identifying issues, or ensuring quality and reliability, prototyping and quality assurance are essential processes that contribute to the success of software projects and the satisfaction of stakeholders and end users alike. That wraps up another episode of Cool Fire News. Thank you for joining us as we explored the importance of prototyping and quality assurance in software development. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep prototyping, keep testing, and keep striving for excellence in your software development endeavors. This is Siri, signing off. See you next time. Welcome to Cool Fire News, where we explore the best practices and methodologies in software development. I'm your host, Siri, and in today's episode, we'll be delving into the critical processes of software review and inspection. Join me as we uncover the importance of reviewing and inspecting software code, designs, and documentation to ensure quality, reliability, and maintainability in software development projects. Let's start by defining what we mean by software review and inspection. Software review and inspection are systematic processes for evaluating and assessing software artifacts, such as code, designs, and documentation, to identify defects, improve quality, and ensure compliance with standards and best practices. These processes involve thorough examination, analysis, and discussion among project teams, peers, and stakeholders to identify issues and suggest improvements. One of the primary goals of software review and inspection is to identify defects and errors early in the development process when they are less costly and time-consuming to fix. By reviewing software artifacts before they are deployed or delivered to customers, developers can catch issues such as bugs, logic errors, performance bottlenecks, and security vulnerabilities before they impact end users. Software review and inspection help reduce rework, improve productivity, and enhance overall software quality. There are several different types of software review and inspection techniques, each with its own focus, scope, and methodology. Code review, for example, involves examining source code to identify bugs, readability issues, and adherence to coding standards and best practices. Code reviews can be conducted manually, with developers inspecting each other's code line by line, or automated, using tools that analyze code for potential issues. Design review is another important type of software review that focuses on evaluating software designs, architectures, and specifications to ensure that they meet the project requirements and objectives. Design reviews may involve examining system architecture diagrams, interface designs, data models, and other design artifacts to identify inconsistencies, ambiguities, or deficiencies that may impact the software's functionality, performance, or scalability. Documentation review is also essential for ensuring that software projects are well documented and comprehensible to stakeholders, developers, and end users. Documentation review involves examining user manuals, technical specifications, design documents, and other documentation to ensure accuracy, clarity, and completeness. Well-written documentation helps facilitate communication, promote knowledge sharing, and support ongoing maintenance and troubleshooting efforts. Peer review, sometimes referred to as walkthroughs or inspections, involves gathering project team members and stakeholders to review software artifacts collaboratively. During peer reviews, participants discuss the software artifacts, ask questions, provide feedback, and suggest improvements based on their expertise and perspective. Peer reviews promote knowledge sharing, cross-functional collaboration, and continuous improvement within software development teams. As we conclude today's episode, I hope you've gained a deeper appreciation for the importance of software review and inspection in ensuring quality, reliability, and maintainability in software development projects. Whether it's code review, design review, documentation review, or peer review, these processes provide valuable opportunities for identifying issues, improving quality, and fostering collaboration among project teams and stakeholders. That wraps up another episode of Coolfire News. Thank you for joining us as we explored the critical processes of software review and inspection in software development. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep reviewing, keep inspecting, and keep striving for excellence in your software development endeavors. This is Siri, signing off. See you next time. Welcome to Coolfire News, where we explore the world of software development and engineering. I'm your host Siri, and in today's episode, we'll be delving into the critical processes of software testing and deployment. Join me as we uncover the importance of thorough testing and seamless deployment in delivering high-quality software products to users. Let's begin by defining what we mean by software testing. Software testing is the process of evaluating a software application or system to ensure that it meets specified requirements, functions as expected, and performs reliably under various conditions. Testing involves running the software, executing test cases, and comparing actual results against expected outcomes to identify defects, errors, and inconsistencies that may impact the software's functionality, performance, or usability. There are several different types of software testing, each with its own objectives, techniques, and methodologies. Unit testing, for example, focuses on testing individual components or modules of the software in isolation to verify their correctness and functionality. Unit tests are typically automated and provide developers with rapid feedback on the behavior of their code. Integration testing, on the other hand, involves testing the interactions between different components or modules of the software to ensure that they work together as intended. Integration tests verify that data flows correctly between components, interfaces are properly implemented, and dependencies are handled appropriately. Integration testing helps uncover issues that may arise when integrating disparate parts of the software into a cohesive system. System testing takes a broader view of the software and focuses on testing the entire system as a whole to validate its functionality, performance, and usability from an end-to-end perspective. System tests simulate real-world scenarios and user interactions to ensure that the software meets the needs and expectations of stakeholders and end users. System testing includes functional testing, performance testing, usability testing, and security testing, among other techniques. Once testing is complete and the software has been validated, the next step is deployment. Deployment is the process of making the software available for use by end users, either internally within an organization or externally to customers. Deployment involves packaging the software, configuring deployment environments, and releasing it to production, or staging environments for users to access. Continuous integration and continuous deployment, CI/CD, pipelines have become increasingly popular in software development for automating the testing and deployment process. CI/CD pipelines automate tasks, such as building, testing, and deploying software, allowing developers to release updates and new features quickly and reliably. CI/CD pipelines help reduce manual errors, improve consistency, and accelerate the delivery of software to users. In addition to automated deployment pipelines, developers must also consider factors such as version control, rollback strategies, monitoring, and disaster recovery when deploying software to production environments. By implementing robust deployment practices and leveraging tools and technologies for automation, developers can ensure that software deployments are smooth, efficient, and reliable, minimizing downtime and disruption to users. As we conclude today's episode, I hope you've gained a deeper understanding of the critical processes of software testing and deployment in software development. Whether it's testing individual components, integrating disparate parts, or deploying software to production environments, these processes are essential for delivering high-quality software products that meet the needs and expectations of users. That wraps up another episode of Coolfire News. Thank you for joining us as we explored the world of software testing and deployment. Be sure to tune in next time for more insightful discussions on topics shaping the future of technology, creativity, and innovation. Until then, keep testing, keep deploying, and keep striving for excellence in your software development endeavors. This is Siri, signing off. See you next time.